Hello, I'm Deyao from King Abdullah University of Science and Technology. Is the mic? Okay. I'm Deyao from King Abdullah University of Science and Technology. Today I'll be presenting our work, motion forecasting with unlikelihood training in continuous space, joint work with Mohamed Zahran, El-Ramli, and Mohamed El-Hosseini. So we focus on motion forecasting in the field of autonomous driving. In this task, the model needs to predict the future trajectory of a vehicle given the past history and some context information. Many state-of-the-art prediction models in this field predict the future as a distribution and trend by a maximal likelihood estimation, MLE objective, or its variant, to maximize the likelihood of ground truth trajectory in its predicted distribution. This simple log likelihood objective here is an example. But MLE objective actually has a limitation. MLE encourages the model to predict a distribution that allocates reasonable probability mass to the region where the ground truth trajectory is located. And because the trajectory distribution domain is over the geometric positions, MLE encourages the prediction to be geometrically close to the ground truth. However, especially in the field of driving, the geometric nearness only is not good enough. In many complex traffic scenarios, there can be many potential trajectories close enough to the ground truth geometrically, but are very unlikely to happen due to the context violation. Let's see a simple example. Assume we have a green car here, driving on a road, and the ground truth feature is go straight, denoted as the green arrow. Let's say we have two different predictions here, denoted as the blue arrows. One is switching to the right lane. The other one is switching to the lane with the opposite direction. As you can see, that the geometric nearness of both predictions with respect to the ground truth is actually the same. So the MLE objective provides the same penalty in both cases. But actually the prediction switching to the opposite direction is quite unlikely to happen and should have a higher penalty. MLE laws cannot distinguish these two cases. Therefore, MLE laws doesn't explicitly and directly encourage the model to follow the context, although the model might take the context information as input already. And which leads to context-violated prediction, highlighted by the yellow circle in the figure. To alleviate this issue, we propose an unlikelihood training objective that explicitly push the model to obey the context. So we have a first question. How to provide a learning signal that can exclude the context-violated region from a predicted distribution? Inspired by the positive and negative data pairs in constructive learning and unlikelihood training, a simple but reasonable way is to directly minimize the likelihood of the context-violated region. Let's first assume we have already a distribution of context-violated future trajectories, P neg of y conditional x, and we can sample negative trajectories from it. So, similar to MLE, but in the opposite direction, we can just minimize the log likelihood of the negative trajectories in the predicted distribution trajectory. But where can we obtain negative trajectories distribution and sample from it? And so we want to exclude a context-violated region from the predicted distribution. We could first sample negative candidates from the prediction, and then check and select out the context-violated ones as the negative data. In this case, the model itself and the context checking procedure together explicitly define negative trajectory distribution. Note that the context checking procedure is used to select out the negative trajectories only, and it doesn't need to be differentiable. And can be purely based on rules like the driving region or the traffic light. Besides, we don't need to introduce any additional learnable parameters here. In our work, we provide and implement a rudimentary map-based checker designed to judge whether a given trajectory is compliant with context and road rules, including the driving region and the driving direction. Here we show one negative example on the left, where the trajectory denoted as the blue line goes out of the driving region, and one positive case on the right that passes the checker. In addition, human drivers also go against the context occasionally. It's 5% of the ground truth in nuisance dataset, and 1% of the ground truth in the other dataset, Argos dataset, also go out of the driving region or to a lane with wrong direction. To allow similar behavior when necessary, we disable the checker when the ground truth trajectory violates the context. Our method can be viewed as an additional loss and can be easily combined with models that output a trajectory distribution. Just simply add our loss, error unlike to the original training loss, error orange. To get a feeling of why our method helps, here we provide a gradient analysis of a new training objective to see how it affects the prediction. Assume a simple single-mode prediction case where the future position at time step t is predicted by a simple Gaussian distribution. And the training objective is a combination of MLE and unlikelihood loss. In this case, the gradient with respect to the predict center mu is in this equation. In the figure below, we use the black dot to denote the location of the predicted center, and the green dot to denote the ground truth, and the red dot to denote the negative. You can see that the first term of the gradient push the predicted center mu towards the ground truth. And the second term pushes away from negative locations. So the center update is affected by both the ground truth and negative. Besides, the gradient with respect to the standard deviation sigma is in this equation. You can see that the change of the sigma depends on the distance from the predicted center to the ground truth, dgt, and to the negative, dneg. In case the ground truth is closer than the -1, sigma will shrink to exclude a negative region and become a better estimation of the true data distribution. In our experiment, we combine our method with two state-of-the-art models. First one is Zahran++. We evaluate the performance in the nuisance dataset. The second one is a distribution variant of Land-Gaussian. We evaluate it in the Argos dataset. To evaluate the distribution quality, we sample 200 trajectories from a predicted distribution and compute the checker violation rate as a metric for the context obeying, and compute the average AD and FDE over these 200 samples to show the distribution accuracy. Denoted as the AD FDE here. When our method incorporated with the Zahran++ in nuisance dataset, we avoid like 16% context-violated prediction and improves the prediction accuracy performance by more than 8%. Here we show two qualitative results on nuisance when combined with Zahran++. White points denote the ground truth feature. In the left example, you can see that the prediction of the blue vehicle highlighted by the yellow circle go out of the driving region when trained without our unlikelihood loss. And our loss help alleviate this issue. Besides, the prediction of the green vehicles here above goes to the line with wrong direction when our loss is not used. And our loss help avoid this violation too. Similar observation is also shown in the right example. Our loss helps reduce the context violation prediction. When combining our method with Gaussian Land-Gaussian, a distribution variant of Land-Gaussian, and evaluated in Argos dataset, we avoid like 56% of context-violated prediction. AD4 and FD4 are reduced by 8% and 6% respectively. So our method helps reduce the context violation and improve the distribution accuracy. Qualitative results of this experiment are shown here. You can see that the prediction without our unlikely loss tend to cover the lane with the opposite direction, as highlighted in the yellow cycle. When our loss is activated, this variation issue is alleviated. Our loss helps to reduce the context variation prediction also in this example, in this dataset. Let's move to the ablation study. So an intuitive way to avoid the context-violated prediction is actually simply removing this prediction as a post-processing step after normal training, right? Even though this is straightforward, the prediction model in this case actually isn't trained to obtain the context violation knowledge. Instead, in contrast, our method encourages the models to understand the context better and to avoid the context violation by itself. Therefore, our model is more intelligent compared to the method just removing the context-violated prediction. And leads to a better prediction. Here you can see that compared to the method simply removing the violation directly, our method still has a lower prediction error. Besides, the model trained by our method can still give us context-violated prediction when necessary. In the second ablation study, we remove the map information from the model inputs and check whether our method helps in this case. Interestingly, our loss still improved the performance shown in the table here. Compared to the baseline model without map input, the model trained by our loss still receives context information from the training signals, therefore it performs better. So, to summarize, in this paper we propose unlikelihood training laws for vehicle motion forecasting that encourage the model to use contextual information by minimizing the likelihood of the context-violated trajectories. And we can combine with state-of-the-art method that predicts the future S distributions. And experiment result shows that our method can improve the quality of the predicted distribution by avoiding context-violated prediction and improving prediction accuracy. So here's reference. Thank you.
Thank you very much. So do we have questions? Can you let me into the microphone? Good. Do we have questions here in the room for Deyao? Okay, maybe I can ask the first question then.
Yep.
So these context violations that are still happening in the predictions, do you have an idea when? Is there specific situations when they are happening, or do you know how to improve those, or is it not clear sort of how to get rid of those?
So currently it's like, because of ground truth, you can see, actually we list the ground truth violation here. It's like in the first data set, the ground truth also violated 5%, and the second is like 1%. So first of all, we think like this is still, yeah, you cannot like perfectly remove it since the ground truth is also violated. The second is that, yeah, our method helps to alleviate this issue, yeah, but still we are not solving it perfectly. So it's still, yeah, we can still achieve the same violated rate as the ground truth.
So do we have questions from the audience? Or online? I don't see any yet. Please quickly go in and type. Yep. Here, please.
Yeah, so, you know.
Let's first repeat the question for the virtual people. So do you find which context violations are actually still violated? Can you repeat? Which are important to avoid.
I think in the motion forecasting setting, the violation we check here, the dryable region is quite important, as you know, many state-of-the-art methods still violate a lot. And yeah, in another context things, for example, like traffic light things, it's also, I think, it's also quite important. But I think this depends on how we design a checker. So if we want to take this into account, we first need to data set. We need data set that provide this information, yes, and then you need a model that can process this information, and then we can apply our learning signal to guide the model to take this into account. But yeah, I would say that a lot of context information, all of them are very important, like traffic light, like speed limit, for example, when you are in high-speed road, and also the driving direction, something like this.
Okay, thanks.
Okay, thank you.
Thanks, Deyao.